Welcome everyone. Today, I, Vedanand Bodas, I'm going to present to you the topic Introduction to Signals and Systems. So, without any further ado, let's get into the topic. So, as you can see on my screen, just yes. So, as you can see on my screen, our topic today is Introduction to Signals and Systems. So let's get into it. So before knowing anything about a topic, we must know what that topic is. So let's understand what is a signal. So a signal is a pattern of variation of some form that carries information. Basically, examples are your waves which travel from point A to point B carrying certain amount of information. Also, other examples are mentioned. Other examples include electrical signals, then acoustic signals, mechanical signals, and video signals. In electrical signals, we all know that voltages and currents carry some amount of electronics or electrical information from one source to another point. And acoustic signals is nothing but sound. So when we create a sound, the sound pushes the air molecules surrounding it, and hence it propagates from certain point to another point, and we hear sound. Similarly, mechanical signals are signals which are caused because of mechanical systems. Here an example is given of velocity of a car. Then video signals, I am talking to you with the help of this camera, which is nothing but a type of signal, intensity level of a pixel. So you're seeing me so clearly because of this very thing. Intensity level of a pixel, camera, video over time also contributes to signals. Now, let's see the next slide. So how is a signal represented? Now, once we know what is a signal, let's see that how is a signal represented. So yeah, so how is a signal represented? So a signal is a mathematical representation that describes a physical phenomena. A signal is a mathematical representation that describes a physical phenomena. The physical phenomena which we saw in the last slide, which is nothing but a signal, is a representation of a pattern which carries information, is represented mathematically or in a graphical method. Mathematically, signals are represented as a function of one or more independent variables, mainly time. For instance, a black white video signal intensity is dependent on x, y, and time t, and which is plotted in this manner, where y-axis is your function or signal, and x-axis represents time. So you can see that when after each change in instance of time, the signal also changes, and hence we can plot this graph over here. So now let's take a look at types of signals. So types of signals are, there are many types of signals, but mainly there are three types of signals: continuous time and discrete time signals, periodic and non-periodic signals, even and odd signals. Now let's get into some details of these three types. First one being continuous time and discrete time signals. So uh, let's go. So a signal is said to be continuous when it is defined for all instances of time. So as we can see in this very graph, that on y-axis it is representing amplitude, and on x-axis it is representing time. So we can see that at every instance of time at x-axis, the value of amplitude is some constant, but the value is available or is defined for all instances of time. Hence, we are getting this continuous type of wave or continuous nature of wave, which is nothing but continuous time signal. Then we see a signal is said to be discrete when it is defined at only discrete instances of time. So in this graph, we can see that the y-axis still represents amplitude, but it is only defined at some discrete instances of time at x-axis, as you can see over here, and for example here. And the amplitude at this very instance is represented by an arrowhead, which suggests magnitude of the amplitude. And as we all know, longer the arrowhead, higher is the amplitude. But the main thing is that we are not getting a continuous graph, since it is only defined at discrete instances of time. So that's basically continuous time and discrete time signals. Now let's get into the next type. Now let's take a look at the second type of signals, which are periodic and non-periodic signals. So uh, a periodic time signal, in this case x of t, is said to be periodic only if it follows this expression, or it satisfies this expression, which is x of t is equal to t plus capital T, which is equal to x of t for the period, or for the value between minus infinity to infinity. Then, oh, I'm very sorry. Then, where capital T is the positive constant that represents the time period of the periodic signal. Basically, capital T is the period after which the signal repeats itself, hence the name periodic signal. Now, as we can see in this graph, uh, from 0 to t, it's kind of like a sinusoidal wave, which is repeating itself with the time period of 0 to t. Hence, this is a periodic signal. Now, let's take a look at a non-periodic signal. So, a signal x of t, in this case, for which no value of time satisfies the condition of periodicity, which was x of t plus capital T is equal to x of t for the region between minus infinity to infinity, is known as a non-periodic signal. So, here are the two examples of non-periodic signal. As we can see in the first example, there is no repetition of signal, which indicates in the first case that it's a non-periodic signal. But also, if we take a look at this formula, x of t plus capital T, here, since there is no repetition, we can't define a period, or capital T represents a period. So here there is no period. So it's a non-periodic signal. And similarly, in the second case, there is once again no repetition, and hence we can't say it's a periodic signal. Now, I hope that you have understood what is a non-periodic and periodic signals. Now let's get into the third type, which is even and odd signal. So a even signal, a continuous time signal, in this case x of t, is called the even signal or symmetrical signal. This is important if it satisfies the following condition: x of t is equal to x of minus t for minus infinity to infinity range. Now, look at this word symmetrical signal. Why so? Because we can see in the formula x of t is equal to x of minus t. Minus t suggests that same signal is represented in the complementary side of which the original signal is drawn. So in the first case, we can see that x of t, suppose let's say this is x of t, so it's represented in positive x-axis as this. But now let's check if this signal is even or odd. So we will put minus t, or let's say we give it some values. So suppose this is going from 0 to 1. So this is x of 1, and this is t. So let's put minus 1 in this equation. So x of t is equal to x of minus 1. So here this signal is being replicated, and it is symmetrical, but it's complementary to the original side, hence it is an even signal. Now let's take a look at this example. The concept would be more clear since here the values are given. So let us consider this first. So here x of t is equal to 0 to 2, suggesting that this distance is 2. So x of 2. Now let's check if it's even. So we will put t instead of t minus 2. So this is the graph which we plot. And since we can see that this is a symmetrical signal and complementary to the original side of the graph, we can say that it is an even signal. So now let's move on to understand what is an odd signal. So as we all can understand, that is the opposite of even, but still, a continuous time signal x of t is called an odd signal or anti-symmetric signal if it satisfies the following condition: x of minus t is equal to minus of xt. So we can see in this case, the axis is reversed, or axis, let me correct my statement. The graph drawn in a specific axis is reversed in its own axis, like plus becomes minus, not a symmetric, it's anti-symmetric. Sorry. So here we can see, let's take a look at this example. let's consider this as the original graph x of minus t. So let's check if this signal is odd. So the minus of x of t will reverse this entire signal in both case, like in x-axis also and in y-axis also. So we can see this is x-axis and this is y-axis. So this is indeed an odd signal. Now let's take a look at what is a system. Since our topic consists of signals and systems, we have I hope that we have understood the basics of signals, what a signal is and what are its types, basic types. Now let's take a look at what is a system. So a system is defined as a physical device that can produce an output for a given input. A system may also be defined as an entity which works on the input signal and transforms it into an output signal. So the input given to a system is called as excitation, and output which comes from the system after the work is done on the input signal is the response. Here it's represented in the diagram. Now let's, as we saw what is a signal and its types, let's like take a look at what is a system and its types. So there are total, like there are many types of systems, but main types of systems are linear and non-linear systems, time variant and time invariant systems, causal and non-causal systems, and stable and unstable system. Now let's take a look in detail of these four types of systems. So let's take a look at the first type of systems, which are linear and non-linear systems. So a linear system is a system which is said to be, or a system is said to be linear if it obeys the principle of homogeneity and principle of superposition. Now you may ask, wait, what is the principle of homogeneity and superposition principle? So I have you guys covered. Principle of homogeneity. The principle of homogeneity says that a system which generates an output, let's say y of t, for an input x of t, must produce an output a y of t for an input ax of t. Now, what does this mean? So, let me show you guys. So, suppose there is a signal named x of t, and which undergoes a transform a system and gives us an output y of t. Now, the principle of homogeneity says that when if we multiply the input with a scalar value, which is in this case, let's take theta. So we must get theta. I'm sorry, if it's theta of x of t gives theta of y of t. This is the principle of homogeneity, which states that if an input of a system is multiplied by a scalar value, in this case, let's say theta, which is a constant value, the output must also be the equal multiplication of the scalar component, which is multiplied in the input. So this is the principle of homogeneity. Now let's take a look at superposition principle, because as the definition of linear system suggests that if it obeys principle of homogeneity and principle of superposition. So superposition principle, according to the principle of superposition, a system which gives an output y1t for an input x1t and y2t for an input x2t must produce an output y1t plus y2t for an input x1t plus x2t. So this is nothing but basically when if we add both of the input signals, if we add both of the input signals x1t, x2t, we must get an output of both of the signals as in summation of the outputs which we will get if we apply only a signal to a system. Like suppose we apply x1t to a system. Let's say this is a system, and we get an output which is y1t, and then we take another system which is x2t, and we get an output of y2t. So when we apply x1t, we get an output y1t, and we get when we apply x2t, we get value y2t. But the principle of superposition states that if we apply the summation of both of these signals, that is x1t plus x2t to a system, system, we must get an output as in summation of the outputs which we would have got as individual outputs which we saw before. So the output must be y1t plus, you guessed it right, y2t. So that's the principle of homogeneity and superposition principle. So a system which follows both of these principles is said to be a linear system. Therefore, for a continuous linear system, ay1t plus by2t is equal to t bracket ax1t plus bx2t. So here we are considering a y1 and y2 as our inputs, and we are multiplying it with the scalar value. Hence, principle of homogeneity, which is followed here, ax1t plus ax2t. This t is the value which is multiplied because of the system, and hence we get a of t bracket x1t b plus b of t bracket x2t. So this was linear system. Now a non-linear system is said to be non-linear if it does not obey the principle of homogeneity and principle of superposition. So it obeys none of this principle. Now this was linear and non-linear systems. Now let's take a look at the next type, which is time variant and time invariant systems. So a time variant system is a system whose input and output characteristics change with the time, is known as a time variant system. If the input and output characteristics of a system do not change with time, it is called as time invariant system. So I have mentioned here some conditions. So this is the condition for the time invariant system, where your y of n of t is equal to y of n minus t. The condition of time variant system is that if this is equal, then we can say that it's invariant. Basically, there is no variance in the signal, input signal and output signal, which means time invariant system. If there is some variance, then it is called as time variant system, where y of n of t is equal to t, which is caused by the system, x times n minus t, which is input change, and y n minus t is the output change. So here I have an example. Let's take a signal y of n is equal to x of minus n as an input. So first we will check for the input change, which is y of n of t is equal to capital T x of n minus t. So this will be, instead of this, we'll put this original signal. So we will get x of minus n minus t. Now, in order for this signal to be time invariant, y of n of minus t, which is the output change, should be equal to x of minus n minus t. So let's check x. Let's put here. So x of minus n minus t is equal to x of minus t, but this minus minus sign, it becomes plus. And hence y of n of t is not equal to y of n minus t. Hence the system is time variant, not invariant, since we are getting since y of n of t is not equal to y of n minus t. So this was the time variant and time invariant systems. Now let's get into the next type of a system, which is, so let's get to the next type, which is causal and non-causal systems. So a causal system, a system whose output or response at any time instant t depends only on the, this is important, only on the present and past values of the input, but not on the future values of the input, is called as a causal system. So for reference, let's write this down. It depends on the present and the past values. Then a non-causal system, a system whose output or response at any time instant t depends upon future values of the input, is known as non-causal. So in non-causal, the output or response at any time t must depend only on future values, but in causal, it should depend on the present and past values. So here is an example. Y of n is equal to 2x of t plus 3x of t minus 3. Now to check for present value, we will put the value of t as 1. So when we will put t as 1, we will get 2 of x, 1, and here we will get 3x minus 2. So this is present and this is your past. So here the system output only depends upon present and past inputs. Hence this example is causal, or if this is an example of a causal system. Then let's take a look at the second example. So y of n is equal to 2x of t plus 3x of t minus 3 plus 6x t plus 3. So Let's put t as 1. The system output is y of 1 is equal to, this will be 1, this will be 1 minus 3, this will be 1 plus 3. So this will be 2x1, this is 3x minus 2, this is 6x4. We can, as we can see, this is present, this is past, and this is future. So here the system output depends on future input, although it contains past and present, but also it contains an element of future input. Hence, the system is non-causal. So that's the difference between the causal and non-causal. The keywords to remember are this. For a causal system, it's the output must contain the present and past values. For non-causal system, the output may contain present and past, but it must contain future values. So that was regarding the causal and non-causal systems. After which we move on to the last type of these systems, which is nothing but, yes, which is nothing but stable and unstable systems. So the system is said to be stable if it follows the BIBO stability criteria. Now you may ask, wait, what is BIBO? So BIBO suggests for bound, that's not right. It suggests for bound input, bound output stability criteria. So a stable system must follow BIBO, whereas the system is said to be unstable if it does not follow the BIBO. So let's take a look at this example and we will understand the concept better. So y of t is equal to x to t. This is a signal. Let the input be u of t, which is, we all know that u of t is nothing but your unit RAM signal. So yeah, so that's a unit step bounded input. Since it's bounded between a certain range, then the output y of t will be u of 2t, which is nothing but u of t, which is nothing but bound input. So hence, for a bounded input, we have a bounded output. This system is stable. But let's take a look at the next example. Uh, y of t is equal to integration of x of t dt. So let the input be u of t, which we saw in the earlier example. It was an bounded input. Then the output of y of t is equal to integration of u of t dt. Now we all know that integration of u of t dt is a ramp signal, which is unbounded because amplitude of ramp is not infinite. It goes on infinite. So this is the ramp signal and this goes towards infinity. Therefore, this is not bounded output. Sorry for the disturbance. So yeah, so as I was saying that integration of u of t dt is a ramp signal which is unbounded since it goes towards infinity, but the input signal was a bounded input since it's a unit step signal. But we are getting, for a bounded input, we are getting an unbounded output. Hence, this system is unstable. So I hope you have understood the basics of system and the four types which we discussed in this presentation. Now, before giving you guys a thank you note, I would like to share with you the references from which I gathered this information. So, reference number one, which from where I gathered the information, is the tutorialspoint.com. You can all check it on your browsers. Then book by LNB OpenIM on signals and systems. And this is basically the compilation of sample chapters and examples which I have covered in this PPT. And at the last and but not the least, I would like to say thank you for whoever who is listening to this PPT. And on the note, I would like to end with a note. Life is like a sinusoidal signal. It consists of crest and troughs. So we must all fight through it. So that's me signing off. Thank you.